friends, welcome to this lecture. In this lecture we will discuss the concept of compatible system of first order partial differential equation, and this concept is very useful in finding the so called very important method of Char-Pit method to solve to find the complete solution of first order nonlinear PDE. So, first let us start with the compatible system. So, here you consider a general nonlinear partial differential equation of first order in xy plane, that is f of x y z p comma q equal to 0. Here we are assuming that z is a function of two independent variable, that is x y. So, where z is equal to z of x y, and we want to find out the condition such that every solution of one is also a solution of another partial differential equation of first order given by the equation g of x y z p comma q equal to 0. So, means what we want to find out? We want to find out a condition under which the every solution of this equation is also satisfying the solution here. And in this case, when we say that every solution of first equation is a solution of second equation, we call these two equations are compatible equations, and we say that f and g are compatible to each other. Actually here in the definition of compatibility, there are several literature in which you find out this definition, that compatible means compatible partial differential equation means that every solution is common, but in some book you will find out that compatibility means that they have at least one solution in common. So, here I will also prefer to have this definition that at least they have at least one common solution. So, it means that we may say that the partial differential equation f of x y z p q equal to 0 and the partial differential equation g x y z p q equal to 0 is compatible to each other if they have at least one solution in common. And once we say that they have one solution in common, then we just want to see that how we can find out that one common solution. For that we assume that the Jacobian of p and q, so here we assume that if the Jacobian j equal to dever f g upon dever p q, which is given as f p g p, f q g q is non-zero. So, here to find out that common solution, we assume that the quantity j, which is nothing but Jacobian of f g with respect to p q, is non-zero. Actually this condition enable us to find out the solve for this equation number 1 and 2 for p and q in terms of say x, y and z. Similarly we can write q as function of x, y and z. So, it means that to find out the common solution, we need to find out the expression for p and q from these two equations, and once we have these expression for p and q, then we say that we can solve equation 1 and 2 to obtain p q in terms of x, y and z, and let us say that p expression for p is equal to phi of x, y, z and q is equal to psi of x, y, z. Now, the condition that the pair of equation 1 and 2 should be compatible then reduces to the condition that the system of equation 4 should be completely integrable. Means the equation dz equal to phi dx plus psi dy should be integrable, and once we say that it is integrable, then we can find out one parameter family of solution given as f of x, y comma z comma p a equal to 0. So, this condition number 5 we can obtain from this, that if z equal to z x y, then you can write dz as zx dx plus zy dy, and zx we are denoting as p, which is given as here. So, we can write phi dx plus psi dy. So, if we can integrate, then we can obtain our integral surface like z equal to z of x y. So, what we want is that once we are able to solve equation number 1 and 2, then once we able to solve 1 and 2 in terms of p and q, and after obtaining the expression for p and q, we put it in this equation number 5, and this, if we are able to integrate this to find out our solution z equal to zxy, then we say that we are able to find out one common solution, and the solution of equation 5 will be the form of f of x y z equal to a, and that will contain an arbitrary constant a. So we say that this kind of a solution is one parameter family of solution here. So here let us take one example. So example 1, show that the equation xp minus yq equal to x and x square p plus q equal to xz are compatible to each other, and hence find a one parameter family of common solution. So first thing we want to show that if they are compatible to each other, so they must have at least one solution in common, and let us find out that they have one solution in common or not. So for that, you first you find out the expression for diver fg or diver pq, and if this quantity is non-zero, then only we can proceed, or we can say that then only we can say that 6 and 7 can be solved for p and q. So if you calculate this Jacobian j equal to diver fg upon diver pq, and it is we have already calculated, and the value is coming out to be x into 1 plus xy, and we say that this will be a non-zero in a suitably defined domain D. So let us define a domain D such that x into 1 plus xy is non-zero. In that domain we can solve our equation number 6 and 7 for p and q. So for example, I can use this xp minus yq equal to x, and we can simply say that xp is equal to x plus yq, and p is equal to say 1 plus yq upon x. So once we have p, then you can write down this as x, this you can use q here. Q here is what? Q, I can say that xp minus x divided by p here. So now once we have the value of p here, you use equation number 7 to get the value of q, and once we have q, then you can solve equation number we can have the value of p and q like this. So let us see whether we are able to solve this equation or not. So let us say that xp minus yq here, so xp minus yq equal to x here, and x square p plus x square p plus q is equal to say xz. So here we have this. So what we can do here, we can multiply by y, and what you will have xp plus yq equal to x, and we have x square yp plus yq equal to xyz. This is minus sign, okay. So now add these two. So what you will get here, we have xp plus x square yp, and these will cancel out each other, equal to x plus x y z. So we can take it x common here. So we have p 1 plus xy, and here it is 1 plus yz. So we can write p as 1 plus yz upon 1 plus xy. So that is what we have written here, 1 plus yz upon 1 plus xy. So once we have p, then you can find out q like this, x into 1 plus yz divided by 1 plus xy minus yq equal to x. So we can say that yq equal to x 1 plus yz divided by 1 plus xy minus x. So if we simplify this, you will get x plus xyz divided by 1 plus xy minus x square y here. So this will be cancelled out here, and here we have yq. So now if we take y common, then what we will get, this y will be cancelled out here and here. So what you will get, here you will get xz, here I think it is x minus x square y here. So what you will get, xz minus x square upon 1 plus xy. So here we can take out x z minus x upon 1 plus xy. So q equal to So here q equal to x into z minus x, x into z minus x upon 1 plus xy, so which we have written here. So so what we have achieved here, that since Jacobian is non-zero, so we solve equation number 6 and 7 for p and q, which we have given that how we can solve for p and q. So once we have p and q, then our next aim is to solve this equation dz equal to p dx plus q dy, and if we see that if this is integrable, then we can say that equation number 6 and 7 are compatible to each other. So you just put the value of p and q, then it is dz equal to 1 plus yz upon 1 plus xy dx plus x into z minus x upon 1 plus xy dy, and we want to see whether it is integrable or not. So here you have to apply your experience, and you say that here if you look at it is x into z minus x, and here in dx we have yz here, and here also we have xz here. So we can simplify this, and we can write this that if you subtract dx from dz, then we can write dz minus dx equal to, so let me write it here, dz minus dx equal to 1 plus yz upon 1 plus xy dx minus dx plus x z minus x divided by 1 plus xy dy, and if you simplify it is 1 plus yz minus 1 minus xy divided by 1 plus xy dx plus x into z minus x upon 1 plus xy dy, and if you solve this, what you will get, here you can take y common, so y z minus x d of x divided by 1 plus xy plus x z minus x 1 plus xy dy. Now you can divide by z minus x, so here we have dz minus dx divided by z minus x, and what you will have here is y dx plus x dy divided by 1 plus xy. So here you got this, that dz minus dx upon z minus x equal to y dx plus x dy upon 1 plus xy. Now you can integrate this directly. In fact, you can say that it is what, d of z minus x upon z minus x, and here you can write this as d of 1 plus xy divided by 1 plus xy. Now when you integrate it, then you will get what, so ln of z minus x equal to ln of 1 plus xy plus some constant, let us take this as ln c or whatever. So here you can say that z minus x equal to c times 1 plus xy. So that is what we have written here, that z equal to x plus c times 1 plus xy, and we say that since we are able to integrate this dz equal to p dx plus q dy, then we integrate means that we are able to find out the expression of z in terms of xy in volume 1 parameter. So we say that this is a common solution of both the equation, and we say that this is a one parameter family of common solution, and since they have one parameter family of common solutions, so we say that our equation f and g, which we have written here as xp minus yq equal to x and x square p plus q equal to xz are compatible to each other, because they have one family, one parameter family of solution in common. Similarly, let us consider one more example. Show that the equation p square plus q square is equal to 1 and p square plus q square x equal to pz are compatible to each other, and then we want to find out a parameter family of common solution. So here I ask you to provide that Jacobian, that is dever fg upon dever pq is non-zero. So here you define f as p square plus q square minus 1, and g you can define as p square plus q square x minus pz. So here we have to calculate this quantity. So it is what? It is fp, fq, gp, gq. So here you can calculate f of p is 2p, f of q is equal to 2q, g of p is equal to, here you can say that it is 2px minus z, and gq is equal to 2qx, that is all. So, we can say that this expression is going to be what? It is 2p and it is 2q, here it is 2px minus z, here we have 2qx here. So, gq is only 2qx. So, when you simplify this, it is what? 4pqx minus 4pqx minus 2qz. So, that is plus here. So, 4pqx minus 4pqx plus 2qz. So, we can say that these cancel out. So, we have 2qz is value. So, we say that this is not identically equal to 0. So, let us define a domain in a way such that this quantity will remain non-zero. So, we say that in this domain D, we say that Jacobian is non-zero. So, it means that we can solve equation number 11 and 12 in terms of p and q as a function of x, y and z. So, here let us solve this, let me write it here. Here we have p square plus q square equal to 1, and here we have p square q square x equal to, let me write it here, it is pz. So, here we have pz. So, if you use equation number 1, then we can write x equal to pz. So, we can write p as x by z here. So, p is x by z, then you can find out the value of q from 1. So, we can write q square equal to 1 minus p square, that is 1 minus x square upon z square, or you can say that z square minus x square under root divided by z, that is the value of q here. So, q is coming out to be under root z square minus x square upon z, and p is coming out to be x by z. Here you can say that we have two value of q, that is plus minus this thing. So, once we have p and q value here, now let us see that dz equal to p dx plus q dy is integrable or not. So, let us put the value of p, that is x by z dx plus q is under root z square minus x square divided by z dy equal to dz. Now, here we want to show that this equation is exactly integrable, or we can say that this is written as d of z. So, we want to say that it is written as gxyz equal to some 0. So, we want to find out the expression gxyz equal to 0. So, for that you see that here you can write down z dz equal to x dx plus under root z square minus x square dy. So, from you can see that I can write z dz minus x dx divided by z square minus x square equal to dy. And if you again you see that it is what? I can write that it is under root z square minus x square equal to dy. So, because if you integrate this, then what you will get? You will get if you differentiate this, what you will get? 1 upon 2 under root z square minus x square, and when you differentiate this, it is 2z dz dz minus 2x dx. So, 2 will be cancelled out, and we have the expression z dz minus x dx divided by z square minus x square. So, this is written as d of under root z square minus x square equal to dy. When you integrate, then what you will get? It is z square minus x square equal to y plus some integration constant, that is c. So, we can write here z square equal to x square plus y plus c whole square. So, that is the solution. You can say that you can write down the one parameter family of common solution like this. So, we have obtained a solution z square plus z square equal to x square plus y plus c whole square, and please note down here that I have taken only the plus value, that is q equal to under root z square minus x square upon z. So, here I have taken only plus value. If you can take the negative sign, so I can write it here z plus minus here. So, here I will write plus minus here, and here you can write plus minus here. So, you can write plus minus here. So, that is the only change when you consider the both the sign. So we can say that here we are able to find out one parameter family of common solution of the equation p square plus q square equal to 1 and p square plus q square x equal to pz. So what we have achieved here, by having one solution in common, we say that these two equations are compatible to each other and the common solution is given by this. So now move back to our problem. Now here we wanted to give one very important remark, because what we have given as a definition of compatible system, that every solution of first PD is a solution of second PD and vice versa. But here in both the example which we have discussed, it is not happening. In fact, if you look at in the first problem, we can verify that in first problem, what is this? Let us look at the first problem. First problem is this: xp minus yq equal to x. Let me write it here. This is xp minus yq equal to x, and the other equation is x square plus p, x square p plus q equal to xz, right. So if we want to see that here this x equal to y, z equal to x y plus 1 is a solution of first but not the second. Let us see that z equal to x y plus 1. So if we see that this will satisfy the first equation but not the second, you can see that here zx is equal to y plus 1 and zy is equal to x. So when you put in equation number 1, so x p is zx, so p is y plus 1 minus yq is zy, that is x, and when you simplify, what you will get is x. So it means that this satisfy this first PD. So it means that z equal to x y plus 1 is a solution of first. But if you look at the second equation is what? X square p is what? It is y plus 1 plus q is x here, and when you simplify this, it is x square y plus x square plus x, and it is not equal to xz means xz means x y plus 1. So when you simplify, it is what? X square y plus x square. So here we say that it is not equal. So it means that z equal to x y plus 1 is a solution of first PD but not the second PD. So it means that though we have shown that they are compatible to each other in the sense that they can be solved for p and q, and dz equal to p dx plus q dy is solvable and in fact integrable, and we have found the one parameter family of common solution. So we say that our solution, our definition that they are compatible to each other, provided that every solution is common, may not be say correct or may not be taken in a precise manner. So similarly we can see one more example. If you look at the second example and we try to see that z equal to x plus y by root 2 is a solution of first equation but not the second equation. For that look at the equation. The equation is p square plus q square is equal to 1. So let me write it here: p square plus q square equal 1, but p square plus q square x equal to pz. So here we want to say z equal to x plus y by root 2. So we say that here if you calculate p is what? P is 1 by root 2, q is what? Q is 1 by root 2, and it satisfies the first equation but not the second equation, because if you look at the second equation, here it will be x equal to 1 by root 2 and z is x plus y upon root 2. So here you can say that these two are not equal. So it means that this will satisfy the first equation but not the second equation. So here we have say problem in the sense that there are two things. First thing is the definition, and second thing is to show that the equations are compatible to each other. So if we take the definition of compatibility as that every solution of first PD is a solution of second PD, then we can say that then the method that they can be solvable for P and Q, and the corresponding equation dz equal to p dx plus q dy is integrable. We can say that if we take this definition as that every solution is common, then we say that the next thing is this is a method to find out one solution in common, because here in both the example what we have shown is that these two equations in both the example 1 and example 2, they have one solution in common. So if we take that definition as that every solution in common, so we simply say that they are not compatible to each other, yet they are having one solution in common. So it means that either we take the definition as that every solution in common and the procedure to find out one solution, one common solution, or we simply say that the compatibility means they have one solution in common. So here we can say debate on this thing. So now let us move next, because what we have shown here, we have shown that given in PD P f equal to f x y z p q equal to 0 and g x y z p q equal to 0, what we have shown that they are compatible to each other, provided that we can solve f and g in terms of p q as a function of x y z, and dz equal to p dx plus q dy is equal to is integrable. But many times it is not very easy to see that how we can solve. So is there any condition available by which without solving the two PDs can we say that our equations are compatible to each other? It means that it is equivalent to say that we can solve f and g for p and q, and dz equal to p dx plus q dy is integrable. So now we want to find out a condition in which we simply use a equation of PD, and by saying by using the equation of PD only, we say that these two equations are compatible to each other or not. So in theorem 3 we will give the necessary and sufficient condition that the two equations are compatible and the corresponding dz equal to p dx plus q dy is integrable. So here this condition is to give that dz equal to p dx plus q dy is integrable. So basically you can consider this as that it is a integrability condition, provided that Jacobian is non-zero. So let us say that, look at the equation number 5. So we say that a necessary and sufficient condition that the equation 5 is integrable is that this bracket fg is equal to 0, where fg is written as Jacobian of fg with respect to xp plus p times Jacobian of fg with respect to zp plus Jacobian of fg with respect to yq plus q times Jacobian of fg with respect to zq, and if you look at the expression, that should come out to be 0. If this value is coming out to be 0, then we say that this dz equal to p dx plus q dy is integrable, and we can say that f x y z p q is equal to 0 and g x y z p q are compatible to each other, provided that Jacobian of f comma g with respect to p and q is non-zero. So this condition along with this condition will simply say that this f and g are compatible to each other, or we can say that they have at least one solution in common. So here we use one condition that dz equal to phi dx plus psi dy is integrable if and only if x dot curl x is equal to 0. So this is the result which we are using, and you can find out this result in study of affine differential equation, and you can see the book of Ian Sinaden to get more information about this condition that x dot curl x equal to 0, where x is phi, psi and minus 1. So let us calculate the quantity that x dot curl x equal to 0. So here x dot curl x means this is x phi I plus psi j plus k into minus 1 into curl x. Let us find out the curl x. This is I j k divided by double x divided by double y divided by double z phi psi minus 1, and if you simplify this, this is coming out to be psi x plus phi psi z equal to phi y plus psi phi z. You can simplify this and you can have this value. Now psi x plus p psi z equal to phi y plus q psi z. Here we are just writing phi as p and psi as q. So we can write that our integrability condition is now reduced to 14. But if you look at this condition 14, it is still given in terms of p and q. So here we if you want a condition in terms of f and g, then we have to get rid of the expression phi and psi here. So for that, let us utilize the equation f and g here. So since p is equal to phi x y z a and q equal to x y z a, that the equation f x y z p q equal to 0 can be written as f of x y z phi psi equal to 0. Now what we can do here to find out the value here, that is psi x plus p psi z and phi y plus q psi z, what we do, we use the equation f and g to find out this value separately and this value separately, and then equate, so that we can eliminate this phi and psi and we can get a condition in terms of f and g purely. So for that you simply differentiate with respect to x, and we have f x plus f p phi x plus f q psi x equal to 0 here. So here we are simply assuming that x y z phi psi are argument to each other, and we are simply differentiating with respect to x, provided that phi is written as a function of x y z here and psi as a function of x, y and z here. So here I am not assuming that z is a function of x. So here we are writing f x plus f p phi x plus f q psi x equal to 0, and then we again differentiate with respect to z here. So f z plus f p phi z plus f q psi z equal to 0, and with the help of this you just multiply this equation number 17 by phi and we can get this equation number 18. Now here if you look at the equation number 18 carefully, then here the term which we wanted to get, the phi x plus phi phi z, and that is what we have written here, this is psi x plus phi psi z. So it is psi x plus phi psi z. So this is the value we can obtain from this. So here we can get this value. Now here if you see, I have and when we differentiate with respect to x, I have taken z as a independent of x y. But if we do not take if we take that z is a function of x and y also, then we can write here the following thing, f of x y z phi and psi equal to 0. Now here let us assume that z is also a function of x y and see what you will get. So in this case we have f of x plus f of z. Now here we have z of x, and here we have f of phi of x, and here phi is a function of z. So phi of z, z of x plus f of psi, and then psi of x plus psi z and zy zx equal to 0. And if you simplify, what you will get, here I am writing f of x plus the zx is p f z plus f of p, and here it is what phi x is, I am writing phi x plus phi z is phi z, and zx is p plus f of q psi of x plus psi z, and this is q, zx is p, so equal to 0. And if you look at, this is the exactly the equation number 18, f x plus p phi z, I am writing here f p phi x plus phi z, I am writing p as phi, so f q psi x plus phi psi z. So it is exactly the equation number 18. So whether you do it like this, that first you differentiate with respect to x, keeping z as a independent variable, z is not depending on x, and then you differentiate again with respect to z, and then you suitably manage with the equation number 16 and 17 to get this equation number 18, or you assume that z is a function of x y and you simply differentiate with respect to x and to get this expression that is given as equation number 18. And the similar expression is valid for equation number for equation g x y z phi psi equal to 0. So, repeating the same process for g, we have g x plus phi g z plus g p phi x plus phi z plus g q psi x plus phi psi z equal to 0. And as we said that we want to get expression for this. So, what we do here, we multiply by f p and here we multiply by g of p and then subtract, so that this term will be cancelled out here. So, when we do that, solving the equation 18 and 19 for psi x plus phi z means that is this thing. What we do here, we and we can get psi x plus phi psi z as follows: f x g p minus f p g x plus phi f z g p minus f p g z divided by f p g q minus f q g p here. So, here this quantity, if you remember, this quantity is the Jacobian of f g with respect to p and q. So, we are calling this quantity as j. So, we can write this as this quantity is what, Jacobian of f g with respect to x p, I am writing here, plus this is Jacobian of f g with respect to z p. So, I am writing psi x plus phi psi z is 1 upon j Jacobian of f g with respect to x p plus phi times Jacobian of f g with respect to z p. So, here we are able to find out the quantity psi x plus phi psi z, and here Jacobian is we have utilized that Jacobian is non-zero. So, we can divide by Jacobian. Now, this gives an expression for the left hand side of equation number 14, and in a similar way we can differentiate f and g with respect to y and z, or when we assume that z is not a function of x y, but we can directly differentiate f with respect to y keeping z as a function of y. Then we can do the repeat same procedure, and we can get the value of psi y plus phi psi z, and it is written as minus 1 upon Jacobian Jacobian of f g with respect to y q plus phi times Jacobian of f g with respect to z q. Sorry, it is psi times Jacobian of f g with respect to z q. And using the equation number 22 and the previous one, that is 20, and equation number 14 where we equate these two. So, using the expression for this and this, and we can write here that using the expression given in equation number 20 and 22 into equation number 14 and replacing phi and psi by p and q respectively, we observe that the two conditions should be compatible such that f g is equal to 0. When you equate these two, we have the following thing, that Jacobian of f g with respect to x p plus p times Jacobian of f g with respect to z p plus Jacobian of f g with respect to y q plus q times Jacobian of f g with respect to z q is equal to 0, and this quantity we are taking as bracket f g. So, we say that if bracket f g is 0, then f and g are compatible to each other, and we say that suppose that condition 21 and 23 are satisfied, then we can solve equation 1 and 2 for p and q, and these obtained functions satisfy the condition that p x plus q y, and this implies that they exist as function z equal to z x y such that p equal to z x, q equal to z y, and this function is an integral of both the equation 1 and 2. So, here the bracket f g equal to 0 is an integrability condition, that dz equal to p dx plus q dy is exactly derivative of a function z equal to z x y, and in this we have already assumed that Jacobian of f g with respect to p q is non-zero. So, it means that we are able to solve f and g with respect to p and q in terms of x y z, so that this equation is integrable. So, this is the method of, this is basically an integrability condition which help us to find out one common family of solution. So, with this I end this lecture, and in next lecture we will discuss some example based on this, and we try to discuss a very important method, that is Chapin method, based on this compatibility concept. So, thank you very much. We will continue in next lecture. Thank you.